Welcome to the Optics Worked Examples. In this section, we will be using the rules for drawing ray diagrams to find out where an image will form. We will also use the mirror and lens equations to find out the same thing mathematically. During these worked examples, I suggest you try pausing the video and seeing if you can come up with the correct ray diagram and try solving the equations on your own. Then click play to see if you have done things correctly. Feel free at any point to skip ahead or refer to the printed notes section provided on Moodle. On a side note, all of the lines I'm about to draw in the ray diagrams are supposed to be perfectly straight, but sometimes they appear a bit wiggly due to the fact that I have a bevel on my tablet screen. So make sure on your page you're always drawing those lines as straight as possible. Looking at what I'm asking you to find here, these three things are the most important things to include on your diagrams. We're going to describe our images as being real or virtual, upright or inverted, and we're going to compare it to the size of the object, being smaller, same size, or larger. I'm also going to give you a few of the variables like focal length and distance to the image and object, height of image and object, to find missing variables with our mirror and lens equation. The first thing to do is ask yourself, what object am I looking at? Am I looking at a mirror or a lens? So these diagrams here with the single line drawn there are all going to be the mirror situations, concave or convex. And if you flip through a couple more pages, you'll see that clearly indicated are some lenses. So just remember that light rays reflect off of mirrors and they will refract through lenses. Here we go. First example, grab your ruler and we're going to start to use the rules for drawing our ray diagrams. So line up the ruler with the top of your arrow here, and I'm going to draw a line that's parallel to the axis, and then that is going to reflect through the focal point. So I put an arrow at the end of that line indicating its direction of travel. The second rule I'm going to use is a line from the top of my arrow, the object there, through the focal point, and then through the side note there. You see how I missed the center of that circle there? So you want to make sure accuracy counts. So line up your ruler carefully, make sure it goes right straight through the center, and then we're going to go parallel to the axes. Where those two lines intersect, we will draw the image. So with your ruler, line straight down, and you're going to form the tip of the arrow at that location. Remember, the lines, they light left the tip of the arrow of the object, so they must be coming together at the tip of the image. So we label that with a capital I. Now, in the box on to the right here, we're going to describe the type of the image. So those light rays are converging, so that's a real image. The orientation, I compare it to the object, and you can see that it is inverted. And the size of the image, you'll see it's a longer value than or a larger value than the object, so larger. Those are the three things that I'll ask you on test day. So the height of the image, the size that I'm talking about, if you took your ruler and measured how many centimeters it is from the base to the tip of the arrow and did the same thing here on the image, you'll see that that's a larger value. That's what I mean by it's a larger image. Now, using our mirror and lens equation, if you look at the variables given down here, if I ask you to solve for the two missing variables, so the first thing we'll look at is distance to the image, di, I'll put a question mark, and I would like to know the height of the image as a question mark as well. So the ray diagram, we could actually measure the number of centimeters of the object and the height, that is, and we could also do the same thing for the image and get an actual measurement off of our ruler in centimeters or millimeters. We can do the same thing with the distance of the object to the mirror, so we could measure that distance to the center, and the same thing with the image distance. So those are the values that we're actually calculating with the mirror and lens equation. So first up, let's find the distance to the image. We're going to use our equation for the focal length is equal to 1 over the focal length is equal to 1 over the distance to the object plus 1 over distance to the image. Solving for di, I'm going to subtract the 1 over do from both sides. So 1 over di will equal 1 over f minus 1 over do. You'll notice that each of these fractions are inverses. So on your calculator, you want to get familiar with the x to the negative 1 button or the 1 over x button. On your calculator here, we're going to practice typing that in just a second, but I want to show you how we're going to type that in here. If I take the inverse of both sides, here and here, it means that I can flip those fractions around. So I'm left with di will equal, and now I'm going to type this in as follows. Focal length is 8 centimeters, so 1 over 8 is the same as 8 to the negative 1. And I'm going to subtract 1 over do, the distance to the object is 1 over 12, or the same as 12 to the negative 1. And I need to take the inverse of all of that. So if you grab your calculator, here's how you should type it in. So I'm going to open with a set of brackets, and I'm going to type in 8, and then here's my inverse button, x to the negative 1. I'm going to subtract 12 to the negative 1. I'm going to close bracket that, and again hit to the negative 1 there, and my answer is 24 centimeters. So I can make that equal to 24 centimeters. So distance to the image, 24 centimeters. We just found that is the distance. 24 centimeters is from here, where we drew our arrow, all the way to the mirror. Next up, let's find the height of the image. So we're going to our other equation for magnification. So hi over ho is equal to negative di over do. I want the distance to the image by itself, so distance to the object has to move to the other side. I'm going to multiply both sides by that value. So hi will equal the negative di times ho all over do. So I've just moved that ho up to the other side, multiplied both sides by it. So don't forget to put that negative in there, so the negative stays on the outside, and I've got distance to the image, which I found to be 24 centimeters. Multiply that by 6, which is the height of the object it tells us in the box down to the right, and divide by the distance to the object, which is 12. Try typing that in your calculator, and you'll see, or in your head, and you'll see that that is a negative 12 centimeters. Now, considering we're talking about the height of the image, what does that negative sign mean in front of that? You can probably guess that tells you that it's inverted. It's pointing down. So again, ray diagram, we use our rules to find our image, and we use our mirror and lens equation to back that up. Example number 2, you'll see the object is placed inside the focal point. So this is one of those special situations where you have to look at your handouts and see that a virtual image is going to be formed. So you have to keep this in mind, because our ray diagram rules will show us this. So first of all, line up your ruler parallel to the axis and draw your first line to the mirror, and then remember that will reflect through the focal point. Now I'm going to leave my ruler there because I know that the light rays are going to appear to come from the other side. So follow your ruler back on the far side with a dashed line indicating the light is appearing to come from there but not actually coming from there. The next rule is that we can use is the third rule, where light rays lined up with a center of curvature will travel to the mirror and reflect straight back. So I just lined up my ruler with a center there. And you'll see that those light rays will be diverging when they reflect back. Again, keep your ruler where it is, and you'll see that we can take those dashed lines and bring them together on the far side. So those light rays traveling back are clearly diverging light rays, and your eye would assume that the light rays were coming together on the far side somewhere over in here. So we would put in our image over there. So the type of image is going to be a virtual image because the light rays are diverging. The orientation is upright. Compared to the object, you'll see that it's facing in the same direction, and the size obviously is larger. Now, in terms of the mirror and lens equation, our unknown values, we need to know the distance to the object, and we need to know the height of the image. So starting with 1 over f equals 1 over di plus 1 over do. I'm going to solve for do in this case, distance to the object. So 1 over do means that I'm going to take the 1 over di and subtract it from both sides. So I'm left with 1 over f minus 1 over di. So do, I'm going to again take the inverse of both sides. So I'm going to have 1 over my 10, which is the focal length, minus 1 over, and you'll see distance of the image is negative 24. I colored over that number there, but hopefully you can still see that. And then you're going to take the inverse of all of that. So on your calculator, open up a set of brackets, inverse of 10, and then you see a minus and a minus. Be careful with that. So that's a plus inverse of 24, and then take the inverse of that. If you type that in, you'll find the answer to be 7.06 centimeters. So knowing the distance to the object, we can use the magnification equation. So hi over ho is equal to negative di over do. And I want to solve for hi, which is the height of the image. So cross multiplying, I'm going to move that ho up to the other side, multiply both sides by ho. So I'm left with negative di times ho over do. I substitute my values in. I've got a negative out the front, and that's a negative 24 for distance to the image, times, you'll see that the height of the object is negative 4. Again, that tells you it's just pointing down. And we're dividing by the distance of the object, which is 7.06 centimeters. Type that in, and you'll find hi to be negative 13.6 centimeters. So you can compare that number there to the object. You'll see that the height of the image is 13.6 and the height of the object is 4. If I asked you to calculate the magnification, then remember that's the height of the image divided by the height of the object. So in that case, you would simply put in negative 13.6 as the height of the image, divide by the height of the object, which is negative 4. That would tell you how much that image has been magnified by. Example 3. So draw your line parallel to the axis. And then we go through the focal point. And we're going to use the third rule, which are lines that are lined up with the center of the curvature of the mirror. Will strike the mirror and reflect straight back. Now if you draw this perfectly, you'll see that those two light rays are running parallel to each other. And that's a situation where if no light rays are coming together, then no image can be formed. When I hand out the mirrors, you'll see that there's a place that you can put your face close to the mirror and you won't be able to see an image of anything. And that's exactly when your face is at the focal point. There's no way that the light can come together in your eye, and therefore no image is being formed. So this whole table up here is pointless, and same with all of this. Example 4. Line up your ruler parallel to the axis, and then through the focal point. Next rule, second rule I would use, is lines that go through the focal point will reflect parallel to the axis. Where those two lines intersect, we see the image is being formed. So label that as an eye. Our object is already labeled. And we can see the light rays were coming together at that location to form the image, so that's a real image. The orientation, compare it to the object. It is inverted. It's pointed in the opposite direction. And the size, if you measured that height with your ruler, you'd see that the image is smaller than the object. Looking at the variables we're given, let's find out what is the focal length and what is the height of the image. So our first equation, 1 over f is equal to 1 over di plus 1 over do. I'm going to solve for the focal length by taking, if we look at the distance to the image, it tells us it's 20 centimeters. So 1 over 20, or 20 to the negative 1, plus 1 over distance to the object, which is 1 over 30, or 30 to the negative 1. Take the inverse of all of that. Type it in on your calculator, and you'll see it being 12 centimeters. So again, the focal length, 12 centimeters, it tells us the distance that is away from the mirror in our drawing. Next bit is looking at the height of the image. So hi We would then rearrange our equation like we've been doing before, multiply both sides by HO, so it would be negative DI times HO over DO. And that would equal then negative 20 times 10 all over 30. If you type that in, it'll be negative 6.7 centimeters. Again, that negative side tells us it's pointing down. Example 5. The object is at the center of curvature. Grab your ruler again, line up parallel to the axis. So parallel to the axis, and then we're going to reflect through the focus. Next rule, you can see I missed the center of that circle a little bit, and that'll affect my drawing. So through the focal point and parallel to the axis. Pretty close to where I should be. If you draw it perfectly, in this case, the image should be right at the same location as the object. So image would be there. And if you go through all of the calculations, you could actually, well, confirm that the distance, so in this case, the focal length is 24. Remember, the center of curvature is always twice that distance there. If you know that this distance here is 24 centimeters, then you know that the center of curvature would be twice that much. So it would be 48 centimeters. So that's one thing that you know about it. But if you look at the drawing too, the distance to the object is 48 centimeters, so that tells you the distance to the image is 48 centimeters. If you don't believe me, try the calculation. You'll see it comes out exactly the same. And you'll see that the height of the object, you'll see that if it's 15 centimeters that the height of the image is, it's exactly the same. If you draw it perfectly, it'll be 15 centimeters. Again, don't believe me, you can try those equations and you'll confirm it that way. So the type of image, see those light rays are coming together, so that's a real image. The orientation compared to the object, it is inverted. And the size of the image, we just can see that it's exactly the same. We can calculate that. Example 6, continuing on with an object that's pointing down, line up your ruler parallel to the axis, and then through the focal point, and then again through the focal point and parallel to the axis. So where those light rays come together, we can form our image. So type of image, those light rays were coming together, so that's a real image. Orientation compared to the object is in the opposite direction, so we say it's inverted. The size of the image is larger than the object if you're to measure it with your ruler. Now let's solve for the two unknowns. We'll find out what is the focal length first, and then once we know what that is, we'll find out what is the height of the object. So our first equation, 1 over f equals 1 over di plus 1 over do, the one we've been using, di plus 1 over do. So f, I'm just going to take the inverse of the distance to the image, so 58.7 to the negative 1, plus I'm going to add the distance to the object, which is 22 to the negative 1. Take the inverse of that, and you'll find it to be 16 centimeters. Now, the next equation is a little more tricky. We have hi over ho equals negative di over do. And your job is to solve for the height of the object. So that's down here on the bottom of the equation. So if you have to solve for those, I recommend you cross multiply both sides to start off. So I'll have hi times do equals negative di times ho. Last step, to get ho by itself, I'm going to divide both sides by the negative di. So negative di comes over here, and I'm left with ho. So substituting in our numbers here, for ho I've got my height of my image, which it tells me is 48.3 centimeters. Maybe I'll just write this out. So for ho I've got hi do over negative di. Subbing in my numbers, height of the image is 48.3 centimeters. Distance to the object is 22. And distance to the image is 58.7. If you type that in, you'll see that that negative is on the bottom. You'll see that that becomes a negative 18.1 centimeters. So again, that height of the object, that negative value, tells us that is pointing down. Example 7 is the only convex mirror ray diagram that I'll show you. The rest, if you see another one, they're all the same. Just keep in mind that light rays reflect off of mirrors and do not go through them. They may appear to, and that's going to be indicated by a dashed line. So grab your ruler and line up the top of the arrow with the mirror, and we'll go straight to the mirror. And then it's going to reflect, using the law of reflection, of course. We're going to line up my ruler with the focal point so I know how it reflects. So line up your ruler with the little circle that's marked with an F on the far side. That's down, of course, here. So that light would actually appear to be coming from there because it would reflect off in that direction there. The solid line is where the light is actually traveling, while the dashed line is where the light appears to be coming from. Now, the next rule that I'm going to draw is the light ray that is headed towards the focus is going to reflect parallel to the axis. So I'm lining up my ruler from the top of the arrow to the focal point that we just have on the far side. So that's over here. And then it's going to reflect parallel to the axis. So it's going to head back to the left. And if your eye was on the left side here, it would think that that light ray was coming from behind the mirror over here. And where those two rays appear to come together is where the image is being formed. So that's why a convex mirror will always produce an image that is smaller than the object, and it's always going to be upright. The key in these ones is to recognize those light rays are diverging away from the mirror, and therefore it's a virtual image. The orientation of the image to the object is in the same direction, so it's upright. And the size of the image is always going to be smaller. The two unknowns that we have to find are distance to the object and the focal length. If you look at the variables given, we have to find out the distance to the object first, which will then allow us to find the focal length. So the first step is using our hi over ho equation to find out what is that distance to the object. So solving for do, I'm going to cross multiply. So do times hi equals negative di times ho. And then last step to get do, I'm going to divide both sides by hi. So hi comes down here and divides out on the left side. So the negative stays in the front. The distance to the image is the negative 5.76. Height of the object is 12. Height of the image is 4.32. It's important that you keep those negatives in with the numbers because you can see that that negative times a negative becomes a positive. Type that in and you'll find that comes out to 16 centimeters. Now you need to know that number so we can go to our 1 over f equals 1 over di plus 1 over do equation. So we can stick that into the distance to the object. So f is equal to, I'm going to take the inverse of di, so that's negative 5.76. Take the inverse of that. Plus that inverse of 16 that we just came up with. And you'll find that the focal length is a negative 9 centimeters. That negative 9 just refers to the focal length being behind the mirror.